All right, here we go. Welcome to physics lesson 5.2. We're going to be learning today about systems of objects. All right, so we're going to be making free body diagrams again, but what we're going to have is we're going to have kind of a couple different objects interacting with each other. All right, today's notes, Adventure Time themed. You're welcome. All right, so here we go. If you are not familiar with Adventure Time, this dude here, that's Finn the human. This guy here, Jake the dog. He's a stretchy dog. All right, so in this example, and all these examples, all right, Finn the human is going to have a mass of 45 kilograms, and Jake the dog is going to have a mass of 25 kilograms. All right, so what's going on here in this example is Finn is just sitting on top of Jake. All right, and our goal is to make a free body diagram for both Finn and for Jake. All right, so what we're going to do, this is just kind of a hint, when you're solving problems like this, when you've got two objects that are interacting like this, you always want to kind of start with the object that's not sandwiched in the middle. So what do I mean by in the middle? Well, you know, the ground is down here, right? You can't see it. I think there's a little note here somewhere. Although you can't see his feet, Jake is standing at rest on the ground. So the ground is down here, right? So Jake is sort of sandwiched between the earth and Finn. Okay, so we're going to start with the object that's not sandwiched in the middle, which in this case is Finn. All right, so every time you make a free body diagram, you start with your force of gravity. So put in your force of gravity. Hopefully by now you know how to find that. That's just going to be his mass, 45 kilograms times negative 10, so negative 450 newtons. All right, now we know that he's not moving, so his net force is 0. So there's something holding him up. Well, take a look at the drawing here. What's holding Finn up? Oh, he's sitting on a big yellow dog named Jake. So this here is the force of Jake. Okay, and it's got to be exactly big enough to make the net force 0. So it's going to be 450 newtons, right? Okay, so there is my free body diagram for Finn the human. All right, over here, I'm going to make a free body diagram for Jake. All right, so once again, he's got a mass of 25 kilograms, so I'm going to always start with my force of gravity. So the force of gravity on Jake is negative 250 newtons. Oh, I should probably make that force smaller, huh? All right, I'm trying to be better about making my forces the right length. All right, so there we go. Force of gravity is pulling Jake down with a force of negative 250 newtons, right? It's just 25 kilograms times negative 10. All right. Now, this is Newton's third law, right? So check it out. Here's the deal. Over here, we know that Jake is pushing up on Finn with 450 newtons, right? So there's the force of Jake pushing Finn, positive 450 newtons, right? Well, that means there has to be a reaction force, the force of Finn pushing Jake with a force of negative 450 newtons, right? That means there's another force here, the force of Jake. No, sorry, force of Finn, sorry. Right? Finn is pushing down on him with a force of negative 450 newtons, right? But again, we know that our dog here, Jake, is not moving, right? So the acceleration of Jake is 0, the net force is 0. Well, why isn't he falling? Oh, because the ground is holding him up. So there's also this normal force. Notice how big that force is. It's got to be big enough to cancel out both gravity and the force of Finn, right? We need our net force to be 0. So what number, what normal force, plus negative 250 plus negative 450 gives us a net force of 0. And so you'll discover it's got to be 700 newtons, right? That makes all the forces add up to 0. Okay? Now, the other thing that you want to do is make sure that you identify action-reaction pairs. And I've kind of already done that here. The two forces that are labeled in green are an action-reaction pair, right? The idea is Jake is pushing up on Finn, and Finn is pushing down on Jake. And those forces are equal and opposite. All right? So that's the way we're going to do this. We're going to color code. Every time we find an action-reaction pair, we're going to label them with, you know, a color other than black. All right? I'll use green. Why don't we just always use green for our action-reaction pairs, okay? All right, so there we go. I guess that's it. All right, so next example. So basically, there's just a whole bunch of these examples, okay? All right, so this time it's almost the exact same thing, except this time, so again, everybody's kind of sitting at rest, right? So what we've got here is this rope is tied to the ceiling. This is a rope if you can't see it. So there's going to be a tension force pulling up there. Okay, we'll call that tension 1. All right, and then there's this other rope connecting the dog, Jake, to Finn the human. So we'll call that force of tension 2. Okay, so we want to make a free body diagram. All right, so what we're going to do is once again start with the object that's not sandwiched in the middle. So this time the object that's not sandwiched in the middle is Jake, right? He's kind of hanging down here at the bottom by himself. So we can always start with our gravity. So your force of gravity is going to be 25 kilograms, negative 10, so negative 250 newtons. I know that he's not moving, therefore the acceleration is 0 and the net force is 0, right? Because they're just hanging there from a rope. That means that the force of the tension from the rope has got to be big enough to make the net force 0. So the force of tension number 2 is going to be positive 250 newtons. All right. Now, really, where's that tension coming from? If you look at the drawing here, the other end of the rope is attached to Finn, right? So I guess the way that I want to have you guys label this is we're going to label this as the force of tension, but it's Finn at the other end of the rope that's providing that tension. So I'm going to put a little F there to indicate that that tension is coming from Finn, right? Okay, so there we go. That is the deal for Jake. All right. Meanwhile, over here we've got Finn. Well, similarly, his acceleration is 0 and his net force is 0, right? So we can start the same way we always do, which is by putting in our force of gravity. He's got a mass of 45 kilograms, so the force of gravity is going to be negative 450 newtons. Okay. Now up here we've got the force of tension number 1. That tension is coming from the ceiling. So I'm going to call that the force of tension from the ceiling. C for ceiling. Okay. And I kind of got ahead of myself here, right? That's what we need to find. We don't know how much tension force that is. All right. So look for your action-reaction pair. So the two objects interacting here are Jake and Finn. So over here, this is the force of Finn pulling up on Jake with a force of 250 newtons. So it's the force of Finn pulling Jake, positive 250 newtons. So the reaction would be the force of Jake pulling Finn, also 250 newtons, but this time negative, right? So put that in your drawing here. Force of Jake, negative 250. All right. So again, those two forces are the action-reaction pair. Notice I labeled them both in green. All right. And so that means that this tension force up here has got to be big enough to cancel out both the 250 and the 450. So again, it's going to end up being 700 newtons, just like it was in the last one. All right. So there we go. That is example number 2. All right. All right, so this time we got a lot going on here. All right, so it says suppose a ball of characters, so that's this. And there's kind of this big ball of characters here, right? It's got a mass of 120 kilograms. All right. And then over here we got Lumpy Space Princess. She's got a mass of 30 kilograms. Okay. So it says the ball of characters has a mass of 120 kilograms. Lumpy Space Princess, LSP for short, has a mass of 30 kilograms. So Finn is pushing to the left, causing everyone to accelerate at 0.4 meters per second squared. So we're going to make a free body diagram for the ball of characters and a free body diagram for Lumpy Space Princess, LSP. And we're going to identify any action-reaction pairs. Okay, so again, we want to pick the object that's not sort of sandwiched in the middle. And actually on this one, it doesn't really matter. It's probably a little bit easier to start for Lumpy Space Princess. Okay, so let's do that. All right, so if we look over here at Lumpy Space Princess, here's what we know. We know she has an acceleration of 0.4 meters per second squared and a mass of 30 kilograms, right? So automatically, oh, I know my acceleration. I'm going to find my net force, right? Just like last chapter. So I'm going to do 30 kilograms times 0.4 meters a second squared. It's going to give me 12 newtons. Okay? So, now, what we want to do with this is, I guess, move it out of the way. There we go. Let's put that down there. Okay. So what forces are acting on Lumpy Space Princess? Well, there's gravity. So the force of gravity on Lumpy Space Princess is going to be negative 300 newtons. There's a normal force holding her up because she's on the floor, right? She's moving horizontally, so we automatically know those guys cancel each other out. All right? Now, if you look at the drawing here, Finn is over here, right? He's only pushing the big ball of characters. He's not actually touching Lumpy Space Princess. So what's pushing Lumpy Space Princess is the big ball of characters. So here we go. There's a force from the ball of characters. Okay? And that's it, right? I guess it doesn't explicitly say. I should have told you to assume that the surface was frictionless. Otherwise, there's not enough information to solve this. So we'll assume that it's frictionless. All right? And so we know that our net force has to be 12 newtons. Well, that means that the force from the ball pushing Lumpy Space Princess has got to be 12 newtons. All right? I should have made that force a little bit smaller. All right? Okay. So that is the force of the ball pushing Lumpy Space Princess. Positive 12 newtons. Okay? That's going to be one of our two forces in our reaction pair, right? Okay? Now, the other object in my action-reaction pair is the ball. So if my action is the force of the ball pushing Lumpy Space Princess, the reaction is going to be the force of Lumpy Space Princess pushing the ball, right? And that's got to be negative 12 newtons, right? Okay? So what other forces have we got? Well, let's see. This is a 120 kilogram ball. Black is terrible, sorry. So that means that my force of gravity has got to be negative 120 newtons. Again, there's a normal force. Okay? And I know the acceleration is 0.4 meters per second squared, which means that my net force is going to be mass 120 times 0.4. So that gives me 48 newtons. Okay? So now the question is, how much force is Finn exerting? So here's the force of Finn. Well, that's our x, right? So check it out. X plus negative 12 has got to add up to 48. Okay? So I think if you figure it out, your x ends up being 60 newtons. All right? So there we go. There is our free body diagram, and the two green forces are our action-reaction pair, right? The big ball of characters is pushing Lumpy Space Princess forward, and Lumpy Space Princess is pushing the ball of characters backwards, right? She's sort of slowing them down. If she wasn't there, the ball would be moving faster, right? All right, so this time, this one is actually the exact same thing as the last one. The only difference is it's a rope instead of them pushing each other. So for this one, I'm just going to put the solution up on the board, and you can try it on your own. So why don't you pause the video here, try this, and then I'll throw the answer up on the board. All right, so here's the deal. Here's what I did. I started with Finn, because he's the guy that's not sort of sandwiched in the middle, right? So why am I saying sandwiched in the middle? So there's two forces on Jake, right? Well, two horizontal forces. There's the force on the rope, and then, you know, the force of tension from Finn, right? So I started with Finn, and so I said, oh, I know his acceleration, multiplied by his mass of 45 kilograms, and that gives you 90 newtons, which means that this should be 90, which means that this should be 90, which means that this should be 140. Sorry, just caught that mistake there. Okay, sorry. I knew his mass and his acceleration, so I found my net force. I put in my force of gravity and my normal force. Since those cancel, that means the force from the tension provided by Jake has to be 90 newtons, right? Because that's what my net force is. That's my only force. It doesn't cancel. Okay? So if there's 90 newtons of tension on Finn from Jake, then there's 90 newtons of tension on Jake from Finn, action-reaction. Also 90 newtons, but negative. So again, put in your gravity, put in your normal force, and then figure out what Roy's force needs to be to give you the desired net force. Okay? All right. So these kinds of problems are a little bit weird here. So we've got this pulley system. I'm just going to do 2 more of these, and then I think we're going to be way over our time here. So we've got 2 forces. Gravity is pulling Finn this way with a force of negative 450 newtons. And it's pulling Jake with a force of 250 newtons, right? I guess technically it's negative. I'll talk about that negative sign here in a second. So the idea is this rope runs over a pulley, so they're either going to go this way or that way. All right? So what we're going to do is we're going to pick one of those 2 directions to be positive and one of them to be negative. Now, which way you pick is positive and which way is negative doesn't really matter. You just need to be consistent. So the bottom line is one of these 2 forces, either this or this, had to be negative. But they're not both negative because they're both sort of working against each other, right? The idea is, in this example, Finn is working on pulling this way, so we'll call that negative, and Jake is working on pulling this way, which is, we'll call that positive. Okay, so this is sort of a weird thing where our force of gravity for this example is going to be positive instead of negative, like usual. All right, so here's the deal. We also know the acceleration, and there's a reason that it's this big, long, stupid number here, but so 2.857 meters a second squared. So I can find the net force on Finn by just multiplying that by his acceleration, right? So, all right, so you get this net force, 128.565 newtons. All right, so what forces are on him? Well, let's see. Oh, you know what I should do? I made a mistake. Let's see. This acceleration is going to be negative, right? Because they're going to accelerate in a negative direction, right? So this acceleration should be negative, which means my net force is negative. Okay, so force of gravity on Finn is going to be negative 450. But the tension from the rope from Jake, force of tension from Jake is slowing him down. So the question is, what force does that have to be to make my net force negative 128.56? Okay, so do your algebra, call that force x plus negative 450 equals negative 128, and you discover that the force of tension from Jake has to be 321.435 newtons. Okay? All right, and then over here at the other end, same thing. Here's my force of gravity, negative 250 newtons. Oh, nope, positive, right? Because that's pulling in what we decided to call a positive direction. Oh my gosh, my eraser doesn't want to erase. There we go. Oh, negative 250. Now, if the force of tension from Jake is 321, then the force of tension from Finn is negative 321.35. All right? Oh, I think that's all of my forces, right? So let's find our net force. You can find your net force by just adding those, right? So let's see, negative 321.435. Oops, I forgot my 4, didn't I? Plus the 250. Oh, why do I keep making this negative? It's not supposed to be negative. That was the whole point. All right, so your net force ends up being 71.435. So I should be able to divide by his mass of 25 kilograms and get the same acceleration, right? So divided by 25, and you do, in fact, get the same acceleration here. Okay. There you go. All right, let's do one last problem. So these ones are kind of the same thing. Here, your net force is going to be 0. It says the system is static, so that means acceleration is 0. Actually, it means the velocity is 0 and staying 0. All right. So you know that gravity and tension on Finn have to cancel each other out. And once you know the force of tension from Jake, you can find the force of tension from Finn. Okay? Oh, real quick, I just realized on this one I forgot to identify my action-reaction, didn't I? Action reaction. Notice they are opposite though, because this tension here is pulling in a positive direction and this one is pulling in a negative direction. Okay, so that's my action-reaction pair on that one. So I tell you what, let's do this. Why don't you try the rest of these on your own, and when I see you in class next, we'll go over them together. All right, dynamite.